So we are starting chapter 4, which is the arrangement of the electrons in the atoms. In the last chapter we talked about atomic structure and where the protons are in the nucleus and neutrons are in the nucleus and the electrons are in the electron clouds. So we will find as we go through this course that it really is all about the electron, because the only thing that's actually participating in an ordinary chemical reaction is the exchange of electrons. They're either going to be gaining, losing, or sharing. In the bonding chapter is where we will learn how they gain, lose, or share, but today we're going to start talking about the electrons and wavelengths and light and how all that exists and works together. So let's start with the development of the new atomic model. We saw the video in class a couple of days ago kind of referring to how it was developed, and this is going to take you a little further in depth into that. So first of all light or all energy is in the form of electromagnetic radiation, and of course that is is coming from the sun. Electromagnetic radiation, or we call it EM radiation, are forms of energy which move through space as waves. There are several types of electromagnetic radiation. Some of them are visible light, which is what we can see, colors of the rainbow. X-rays, of course, that's what if you have a broken arm and you go get an X-ray machine. We've got ultraviolet light, that's what gives you a sunburn. You have infrared light and radio waves. There's others, those are just a few, and we're going to see the spectrum in a minute. All of the light, regardless from the lowest energy to the highest energy, they all move at the same speed, and that is the speed of light, and it is a constant, and it is 3.00 times 10 to the 8th meters per second. The speed of light is equal to the frequency times the wavelength, and you have that little box in your notes to fill in this formula, where frequency is V, or sometimes in physics you'll see it as an F, like a lowercase f. I'm not really sure why physics uses an F and we use a V. Frequency for F makes more sense, but we have to keep high school students confused. But anyway, frequency is the number of waves passing a given point in 1 second, and we measure that in seconds minus 1, or hertz, or sometimes you can even see it as 1 over second. So sometimes you'll see it like that. The wavelength is that funny looking upside down curvy Y, is the distance between peaks of adjacent waves, and that is going to be measured in meters, or often we'll see it in nanometers. And of course, if we're going to see it in nanometers, we have to remember that 1 meter is equal to 1 times 10 to the 9th nanometers. So you will need that on your worksheet. So 1 times 10 to the 9th nanometers is 1 meter. And then the speed of light is a constant, and so the frequency times the wavelength is also a constant. So what that means is that they are inversely proportional. And of course, if something is inversely proportional, that means if one of the parameters goes up, then the other one has to go down, because they always are going to be equal to a constant. So if the frequency, let's say frequency increases, that means that the wavelength would decrease, or vice versa. If the frequency decreased, that means the wavelength would have to increase, because they are always equal to this 3 times 10 to the 8th meters per second. Okay? So inversely proportional, that's going to be important. Make sure you remember that. So here is a look at what the wavelengths and frequency would look like. If you have a very long wavelength, meaning a high wavelength, you're going to have a short frequency. So you can kind of think of this like if I had a post right here. These are waves on a beach, and let's say this is my pier. If I have a very long wavelength, the waves are not going to hit the pier as often, so they would have a low frequency because they wouldn't hit as often. But if it was a short wavelength, say a choppy day, the waves are going to hit with a lot more frequency. So you would have a shorter or a lower wavelength, but a higher frequency. So if I give you a formula, you know that means we're going to do some problems. So let's do this example. We're going to find the frequency of a photon with a wavelength of 434 nanometers. So we know that we have the speed of light equation, and I'm going to switch to white. I think that might be easier to read on this dark blue background. So we have the speed of light equation. We know that c is equal to 3.00 times 10 to the 8th meters per second. So that is a constant. So we will not be using that to determine our sig figs in our answer. What we will use is the wavelength, because that's what's given to us. So of course this has 3 sig figs, so that's what we want to put our answer in. So the first thing I notice is that my speed of light is in meters and my wavelength is in nanometers. So I'm going to need to do that dimensional analysis and convert from nanometers to meters. So I'm going to take my wavelength of 434 nanometers, and earlier we said that 1 meter is equal to 1 times 10 to the 9 nanometers. Easy way to remember that is they both start with an N, 9 and nano. So I'm going to convert that and do 1 times 10 to the 9 nanometers is equal to 1 meter. So my nanometers will cancel out, and when I put that in my calculator, I would get 4.3 times 10 to the negative 7 meters. So not very long in terms of what we think of as a meter. So now I'm going to take my equation. I'm solving for frequency, which is the V. So I'm going to rearrange and say V is equal to C over wavelength. So now I just plug everything in. So frequency is going to be equal to 3.00 times 10 to the 8th meters per second over my converted wavelength of 4.34 times 10 to the negative 7 meters. And my meters cancel out, and I'm left with seconds to the minus 1, or 1 over second. Okay? Whenever you see that minus 1, that just means it's supposed to be on the bottom, and a lot of times they'll just write second minus 1, but it's the same thing as 1 over seconds, which is the same thing as a hertz. Okay? So I put that into my calculator, and I get that my, oops, I kind of didn't leave myself much room, did I? We're going to write it crooked. 6.91, because I need 3 significant figures, times 10 to the 14th, seconds minus 1, hertz, 1 over second, however you want to do that. So that would be my answer. I'm going to kind of circle that with that unit, and that's how I would work the problem if I was going to solve for frequency. So let's do another one. Let's do the next one, which is going to now have you solve for wavelength. So same equation, going to use C is equal to wavelength times frequency. This time I'm solving for wavelength. So I'm going to say that wavelength is equal to C over V. So now I plug in what I have. Remember that a hertz is the same thing as a second minus 1, or 1 over second. So I'm going to type in 3.00 times 10 to the 8th meters per second. And then I'm going to divide by my frequency. So my seconds will cancel out. And when I plug that into my calculator, I will get 5.88 times 10 to the negative 7 meters. And so because it doesn't specify, I could leave it in meters. So this could be my answer. Or if I wanted to get an idea of how that compares to visible light, I would go ahead and say in nanometers. So I'd say 1 meter, 1 times 10 to the 9 nanometers. That would be the equivalent of 588 nanometers. Now, on your homework, if it doesn't specify, you could leave it in meters. Okay? But if it does specify, you'd need to put it in nanometers. Okay? So that is the speed of light equation. One of the biggest things I need you to remember from that is that wavelength and frequency are inversely proportional. Sometimes you might see it as an indirect relationship, and that's okay too. It just means if one goes up, the other one goes down. So that's going to be an important thing to remember. All right, so we've been talking about the electromagnetic spectrum. So here's what it looks like, okay? Visible light is a very, very small portion of the electromagnetic spectrum. If you look right here, it is just this tiny little, oops, don't need to be in white now. It's this tiny little section right here that's the visible spectrum. So it's not actually very much of the electromagnetic spectrum. So what I want you to pay attention to is the wavelength and the energy, and it doesn't really have the frequency on this chart, but if you look at the size of the waves, you could see that when we're down here and we have a very short wavelength, we have a high frequency because they're coming very often. And we get down here and we have a very long or high wavelength, and our frequency would be much less. And then, of course, definitely need to pay attention to the energy. Okay, so the highest energy waves are the gamma rays, and those are the ones that are extremely detrimental to human tissue. If you are a Marvel fan, the gamma rays are what hit the Hulk. So just a little nerd humor there for you. Radio waves, of course, are much longer and lower energy. We have radio waves coming through our home all the time, and TV waves, and those do not harm us like gamma rays. So that's one way to remember that. They're lower energy. The higher the wavelength, or the larger the wavelength is, the higher the wavelength means lower energy and lower frequency. Short or low wavelengths mean high energy, high frequency. Okay? And in our visible light, one of the ways that we can remember the order, because we're going to remember when we see a rainbow, and if you were a kid, you probably remember Roy G. Biv for the order of the rainbow. Okay, now we're used to seeing a rainbow in the sky and it's red, orange, yellow, so red is at the top, but that's the less energy. Okay, so it's, when we see a rainbow, it's actually a little bit, it's reversed from this. So this would be the top of the rainbow and this would be the bottom, and that's what we're used to seeing. And that's just a way that kids all over have remembered when they want to, hey mom, how do I color a rainbow? And you tell them Roy G. Biv so they can remember red, orange, yellow, green, blue, indigo, violet. Okay? So let's continue on. Let's go back to that. I want to look at that. So a while ago on that last problem we worked, we went ahead and converted it to 555 nanometers. And so that would be right about in here. So it'd be kind of a greenish, between green and blue. Actually, probably between green and yellow. It's more right here, isn't it? So kind of a greenish yellow color would have been that color that we just calculated for on the last problem. All right, so let's talk about light and energy and the photoelectric effect. Electrons are emitted from a metal when light shines on it. We know that, shiny metal, right? Incoming electromagnetic radiation on the left side of this picture is hitting or striking the metal, and it's doing so with enough energy that ejects electrons, and they are depicted as kind of coming off the surface of the metal. Oops, hit that too fast. And then those radiant energy is transferred into the units that we call quanta or photons, and we're going to talk about that further. But basically, light hits it with sufficient energy, ejects the electron, and it's emitted as light in the form of a photon. When a specific amount of energy is exposed to the atom, the electron jumps from its ground state, which is the lower energy state, up into an excited state. And so that's what's happening here. Got a ground state electron, it's going to be hit with enough energy, and then it's going to make that electron jump up into a higher energy level. And so it's going from the ground state to the excited state. When that excited electron returns to its energy level, because we know what goes up must come down, and so when that electron falls back down to the lower energy level, it is releasing energy in the form of light, and that's how we see light. So there it goes falling back down, and of course that travels at the speed of light, which is 3.00 times 10 to the 8th meters per second. We call that an emission spectrum. So a while ago we talked about a photon, and here is the definition of a photon. It is a particle of energy having a rest mass of 0, so basically no mass, rest mass of 0, and carrying a quantum of energy. That quantum of energy, what you need to know, is a specific amount based on the material or based on the amount of energy that originally struck it. So that quantum is the minimum amount of energy that can be lost or gained by an atom. So the energy of a photon, we talked about the quantum that can be lost or gained by an atom. And so now the energy of that photon is directly proportional to the frequency of the radiation. And if you were paying attention in that spectrum of the electromagnetic radiation, we saw that high frequency meant high energy because they are directly proportional. So if frequency goes up, so does the energy. If frequency goes down, then so does the energy. So that is a direct relationship. So that brings us to another equation, which you need to put in the box of your notes, and that is energy is equal to hV, which V is the frequency, and H is something called Planck's constant. Whoops, sorry about that. And Planck's constant is 6.626 times 10 to the negative 34 joules times seconds. And joules is a new unit for us. That J is joules, and it's spelled like this, Joule, and it is a type of energy, okay? Or it is the unit of energy, not a type of energy, I apologize. It is a unit of energy. And so, of course, if I'm giving you some formulas, I'm going to do an equation. The frequency is the same frequency as in the speed of light equation, so it's still going to be measured in hertz. 1 over second or second minus 1, however you prefer to write that. So let's do an example. So we find the energy of a photon with a frequency of 4.57 times 10 to the 14th hertz. So we're going to use hV is equal to energy, where H is that Planck's constant, 6.626 times 10 to the negative 34 joules times second. Okay? That will be given to you on a test. I will not expect you to memorize that constant. Same thing with the speed of light. I'll give you that on a test as well. So we're simply going to plug that in. So 6.626 times 10 to the negative 34 joules times second gave us our frequency. Remember, that's the same thing as seconds minus 1. Oops, that does not look like that. Let's try that again. Minus 1. Okay, and then we're going to plug in 4.57 times 10 to the 14 second to the minus 1. So my seconds cancel out. So I am left with my energy being 3.03 times 10 to the negative 19 joules. And that would be my answer. Okay? So let's see how much you were paying attention or how much you notice about those two formulas. So we're going to do, basically in the next problem, we're going to combine the two formulas, okay? This one wants you to find the energy of a photon with a wavelength of 690 nanometers, okay? So I have the energy equation, which is E is equal to HV. I have the only other equation that has the speed of light or not the speed of light, wavelength is the speed of light. So it is that, okay? And if you notice, what do they have in common? What they have in common is frequency. They have frequency right here in common. So if I were to take the speed of light equation and say frequency is equal to the speed of light over wavelength, I can substitute that for that frequency. So then my formula would look like this. Energy is equal to h, speed of light, over wavelength. Now, if you don't like that, if you don't want to use it that way, you can solve them two separate equations and then you can solve the speed of light for frequency and then plug it in, or you can save yourself some time and do it this way. It does not matter to me which way you do it, but I will tell you this way will save you some time. So now we can plug everything in. I'm going to switch back to white so we can see it better. I know that my wavelength is going to have to be converted because it's nanometers. So 1 times 10 to the 9 nanometers over meter. So that's going to be 6.90 times 10 to the negative 7 meters. So now let's plug everything in and get our answer. So we have 6.626 times 10 to the negative 34 joules times second, times the speed of light, 3.00 times 10 to the 8th meters per second, divided by 6.90 times 10 to the negative 7 meters. Cancel, cancel, seconds cancel, so I'm left with the joules. And when I plug that in, I should get, well, it's 2.88 times 10 to the negative 19, and then that was in joules, so we can see that. So that is my answer. Now you have some homework, or you have a worksheet over all these equations. We are going to work those. You're watching this as a flipped lesson, and so you'll watch we'll be able to work on that all during class tomorrow. So I think we have just a tiny bit more of notes. And I apologize, I know this is a little bit of a long lesson, but we have just a tiny bit more, and then we'll stop. That brings us to the wave-particle duality, and that is something that Einstein discovered and said that energy, we thought, can be travel as waves through space, but it also can be thought of as a stream of particles. And each particle has one quantum of energy. And remember, we said quantum was a specific amount. We talked earlier about the ground state. We talked about the electron coming from the ground state, absorbing energy, and jumping up to the excited state. So the ground state is the lowest energy state of an atom. And then the excited state is the state at which the atom has higher potential energy. In other words, it's absorbed energy and jumped up to a higher energy level. And it stays up there, but then, of course, what goes up must come down, and so then it falls back down into the ground state. And an example of that is neon lights, and that's why we see the bright neon lights. We talked a little bit about the emission spectrum. We said that when that light is given off by the excited atoms as they return down to the lower energy state, we call that the bright line spectrum. And a spectroscope, if I put it through something, it will separate those kind of like a prism, and it will separate and reveal the particular colors of light that passes through the prism and their specific frequencies. So when light is given off, we see it as the visible spectrum, we see it as white light, but actually it's the presence of all the lights, or all the colors of the light. So this is what the hydrogen line spectrum looks like. Those are specific wavelengths at which the energy that's given off, and the colors correspond to the number of energy levels. The more energy levels, higher energy means that it absorbs more energy, and so it equates to a shorter wavelength. Okay, has a definite frequency, a definite wavelength. Here is that equation that I just showed you, how we can substitute. We're going to talk briefly about the Bohr model because we already did talk about that, and that was the one where the protons and the neutrons are in the middle, and then the electrons are in specific energy levels and they're circling around the nucleus. He called those orbits or energy levels. Electrons can circle the nucleus only in allowed pass or orbits. He said that the energy of the electron is greater when it's further away from the nucleus. And the atom achieves the ground state when the atoms occupy the closest possible positions around the nucleus. And then electromagnetic radiation is emitted when electrons move closer to the nucleus. In other words, when they're dropping from the excited to the ground state. This is what we classically draw atoms to look like, is the Bohr model. That's what we see everywhere, nuclear symbols, caution and all that. Here are the energy transitions of an atom, they are fixed and definite quantities. In other words, it's not just random. Energy transitions occur in jumps of discrete amounts of energy, and the electrons only lose energy when they're moving to a lower energy state. So if you look at this, it's called we've got the Lyman series, the Bauman series, and it's just showing amount of energy dropping, and these are energy levels. So these would be the ones, the n=1 would be the closest to the nucleus, and these would be the furthest from the nucleus. And so they're corresponding to the energy level drops. Now, what I want you to understand, and that's what these are showing, is let's look at the last line in all of these. This is dropping from N7 all the way down to N1, but I can also do N7 to N2, N7 to N3. So it doesn't have to fall all the way back down. It can just fall between particular energy levels. In other words, I could go from N6 and I could fall to N3. It doesn't have to go all the way down to 1. So I want you to understand that. But when they're doing that, they're corresponding to specific energy levels. So especially if you look at this in the colors, the red is the longest wavelength on the electromagnetic spectrum, but it's the lower energy. So that's only corresponding to 1 level drop. Whereas you go up here to the purple, up here, and it's a higher energy drop, and it's corresponding to a shorter wavelength. Now, the shortcomings of the Bohr model was that it does not work for atoms larger than hydrogen. That means more than 1 electron. Also, it didn't explain chemical behavior. And so that is where we're going to stop, because that's going to take us into the quantum model, or the current model of how we understand electrons to behave. So thank you for listening. Again, apologize that it was so long. So I shall end with a joke. And it is this: why is hamburger, ground beef, hamburger meat, cheaper than steak? Because the hamburger meat is in its ground state. All right, that's it.